Health Gen AI. We're recording. Welcome everyone to the Gen AI and Healthcare talk series. It's a pleasure to have Pranav Rajpurkar joining us today. Pranav is an assistant professor at Harvard University and works on AI in the medical domain and focuses on medical image interpretation. And his research lab strives to develop AI models that can match the proficiency of top-tier medical doctors and are working on this so-called generalist medical AI system that can resemble doctors in their ability to reason through a wide range of medical tasks. He's written many articles in venues such as Nature, NEJM, Nature Medicine, has been recognized as an MIT Tech Review's Innovator Under 35 in 2023, Nature Medicine Early Career Researcher to Watch, and also has received the Google Research Scholars Award, Forbes 30 Under 30. He leads a number of educational initiatives, including the Harvard-Stanford Medical AI Bootcamp program. And before joining Harvard, he earned his BS, MS, and PhDs, all from Stanford University in computer science. Today, he's going to talk to us about AI in healthcare as it relates to this generalist medical AI. The generalist medical AI will see you now. So take it away. Thank you.
Thanks, John. That's a very kind intro. I thought I'd start today by just sharing a little bit about the worldwide activity across the different fields within medicine. And it's really quite astounding where this work is happening. So the first thing to maybe notice in this picture is this is really a global effort. And what this graph shows is the trials and the number of trials being led in different countries. And we can see the US and China having a large chunk of those, 31% and 29% respectively. But what was interesting is also in terms of the specialties, we're seeing a lot of these trials being gastroenterology, followed by radiology, and then all sorts of other specialties that's going on. And many of these AI trials are showing a benefit in the clinical outcomes. About 75% of the positive results measure the performance of assisted clinicians versus unassisted clinicians. And only about 12% of these trials are showing no improvement. So when I think about how we segment out the progress that's happened to identify where we've made most progress, medical imaging really comes out on top. And here, the goal of applying AI has been to reduce the errors, the time, and the burden associated with the interpretation of this data. There have been algorithms that have been developed and FDA cleared to be able to triage films that have urgent findings to the top of a work list, be able to detect and localize abnormalities, and also to be able to locate and quantify those abnormalities with a few canonical examples that I've shown on this particular slide. And I would like to share for the first part of the talk today how progress have happened along three axes: the algorithms axis, the data sets axis, and the human AI collaboration axis. I'll start with the algorithms. And it was just maybe 6 or 7 years ago that we saw some of the first demonstrations of expert level medical AI algorithms. And these really set the feasibility for clinical use of medical AI. One early study I was involved in looked at chest X-rays and our ability to identify pathologies at the level of experts. Another study that I was part of looked at single lead ECGs and our ability to identify abnormal heart rhythms at the level of performance of cardiologists. And what this established feasibility helped us do is it spurred real-world deployments because it was clear that from a research and technological perspective, these were de-risked. And as an example, a prototype that we developed to be able to snap a picture of a chest X-ray and get an answer on your phone within a few seconds made its way into an algorithm that was developed and deployed as part of an initiative to help with COVID and imaging interpretation at the time. And then the ECG algorithm that we developed got FDA approved through iRhythm, which licensed our technology. And today there are hundreds and hundreds of FDA-approved devices for medical image interpretation, with a high hundreds in radiology. But in some ways, the established feasibility is still simplistic. One example where we are lacking in this feasibility is our ability to compare studies across time, where if you look at the current paradigm on the left, we see that there's much to be desired in terms of our ability to know how this progression from a ischemic stroke to a hemorrhagic transformation is happening, while an AI model that can hypothetically look at all of these scans and the sequence in which they were acquired, it would be able to make that judgment quite accurately. So that's the algorithms. I will chat a little bit about the data sets. It's no secret that the curation and public release of large-scale data sets have enabled lots of advancements. And part of these are what we call domain-aware advancements, where because we have data of a particular type, we're able to leverage what's unique about that data to be able to advance algorithmic development. And that was the case with a large data set of chest X-rays that we released called the CheckSpurt data set, which led to advances in terms of how we do self-supervised learning, how we do transfer learning, and also how we learn when to have AI make an assessment versus when to defer that to an expert. So that's one side of having data sets. The other side is these data sets can help us understand generalization gaps. So for example, we're able to tell patterns in the composition of the training set and how we find that affects the difference in performance on different subpopulations on the test set, whether that's for a race or ethnic bias, or whether that's for a sex or gender bias. Or we can look at questions like what happens when you take an algorithm from one hospital and apply it to another hospital. And that generalization question really remains one of the most paramount for medical AI, where from a transparency angle, from a clinician AI collaboration angle, and from a what happens once you deploy this algorithm in the real world angle, we really need to establish safeguards that allow us to say something is generalizing effectively. And one advance that we're trying to make in the field is what we call the Medical AI Data for All initiative, where we're collecting data sets from all around the world, medical imaging data sets with associated annotation information and metadata, to be able to assess what happens when you have algorithms that are developed in one part of the world applied to another, and what it takes to make them actually work globally. Finally, on the human AI collaboration front, one of the big paradigm shifts is in terms of thinking about model performance versus clinicians to model performance when it's assisting a clinician, or rather the clinician performance when they're being assisted by models versus their performance without model assistance. And as an illustration of this, a typical reader study has some cases which are presented to clinicians with AI and others which are presented without AI, as you would see on the left and right respectively. And what we measured in this experiment was when we gave clinicians a likelihood, in this case of TB, along with the regions that are most consistent with TB on the image. And we gave them some training cases in order to have them get accustomed to the model and how much they should rely on their predictions. What we found was that the clinicians got better with the tool, but that if we had the algorithm run by itself, it outperformed the clinicians when assisted by the algorithm. And this was surprising to us at the time, but in fact, there are now quite a few studies that demonstrate that the algorithm independently is surprisingly better than the clinician using the algorithm. And what this brings up is that there's inconsistency in the benefit that is given to clinicians as a result of AI assistance. And the factors that underlie this benefit is really something that's still an open question today. An ongoing study that we actually just published in Nature Medicine a couple of weeks ago investigated what is it about the characteristics of people and about AI that can help predict whether or not there's going to be benefit when an AI tool is used by a particular radiologist. And one of our findings here was that when the AI is wrong, you can severely hurt the performance of clinicians, as opposed to when it's right, we can end up in a case in which we only marginally help the radiologist or the clinician that's using the tool. So the takeaway here is that this idea that just because we have expert level AI, we're going to improve clinician performance is actually a little bit misguided. And we need to be thinking about the experience level, the interaction, the case difficulty, and the automation bias. So there's been promising progress in the last 5-6 years. And on the algorithm side, on the data set side, on the human AI side, I just went through a few of the factors that have both demonstrated the progress as well as the opportunity for this next generation of medical AI. And so I want to make some predictions and claims about the next 5 years of medical AI along the same fronts. Today, medical AI is in the age of narrow specialized solution. We have, for a modality, usually an algorithm that can solve one particular problem, detecting brain aneurysms or appendicitis, or detect an ACL tear, or differentiate between two cancer subtypes. But when we think about what doctors do, they're comprehensive and they're context-driven, versus narrow AI, which is really doing very specific tasks. There's a big gap in terms of what we expect from people and from the current age of machines. But I think in the next 10 years, we will expect AI to be able to do what doctors can do and even more. And this is what we call the vision for the generalist medical AI, which are doing the tasks that are comprehensive and context-driven as doctors do. But on top of that, going beyond what is known in medical literature in terms of our ability to make risk predictions and treatment suggestions that are truly smart and data-driven. Generalist medical AI informally refers to AI models that can tackle the full spectrum of tasks that doctors can do and more. So I want to highlight a few of the capabilities that we talked about in a paper that we published last year that defines GMAI. And these are dynamic task specification, multimodal inputs, and multimodal outputs. And it'll become clear what each one of these means in a few slides. So I'm going to start with dynamic task specification. Conventional AI, you typically get an image, and then you say something like 95% likely to be a mass, excuse me. This is because the model's been trained to identify masses on CT or MRI scans. But let's say you have that MRI scan with the query, is this mass appearing on the head MRI scan more likely to be a tumor and abscess? And you can have the GMAI model come back to you saying that this is showing a large astrocytoma brain tumor rather than an abscess. And the dynamic part here is that I can ask a different question or a query and have the model answer that for me without needing to be explicitly trained for that particular task. Capability number 2 is multimodal inputs, where the idea is, in this particular case, it's only by looking at the combination of the imaging, the case vignette, and the lab values is my model going to be able to say that these factors are supporting a diagnosis of rheumatoid arthritis. And here's the evidence in each one of these pieces that's helping me rule out other possible causes. There's been a lot of advance in our ability to handle multimodal data in the past couple of years. And in particular, our models are able to think about different data types as being represented in a similar format in computer language, such that we're able to use a common architecture and a common training procedure across these very different kinds of data sources. Multimodal outputs looks at the other end of the model, the output end, and here we can have a model look at very different pieces of information and be able to make an assessment in language to say this patient is presenting with chronic heart failure that's exacerbated by acute symptoms, and as an explanation, be able to reference back to a part of the image or the input and say, here's the clip of the echo that's showing the reduced ejection fraction. And so that's the multimodal output side of things. The vision for the Generalist Medical AI is to be able to combine the non-imaging data with the imaging data and the clinical history to produce these customized interactive reports for the radiologist, for the physician, and for the patient. And that's the vision we highlighted in our New England Journal of Medicine review late last year. So I want to share why I think the following is feasible in the next 10 years and how we're already seeing early sparks of generalist medical AI. And I want to start with this study called Check Zero. And in Check Zero, what we did was we trained a model to be able to identify diseases in images without explicitly training for particular diseases, but instead by showing it pairs of images and their associated radiology reports to be able to learn a useful representation, which can then be applied for zero-shot disease detection. At inference time, to ask whether an image contains a particular pathology, you can pass in two prompts, one that says the name of the pathology and another that says no before the name of the pathology. And you can see which one of the two prompts matches the image better when encoded by the text transformer and the vision transformer, respectively. And in this case, because the negative prompt has a higher similarity, we can say that this image doesn't have that particular pathology. What we showed was that with this method, we were able to outperform previous self-supervised approaches and get close to the performance of fully supervised approaches, which are actually explicitly trained to say, for this image, this pathology exists, for this image, it doesn't. And that's pretty powerful. The key result was that our model was similar to radiologist performance, even though we were evaluating it in this zero-shot manner without explicit training for these particular pathologies. So we can take this one step further. We thought, if we can match images with associated reports, could we set up a retrieval system such that we can actually output reports for any new image? And that's what we call CXR repair, where in CXR repair, we're able to encode an image. We look at a database of a bunch of reports. We encode all of them, and then we see which one of those texts matches our image best, and we make that our prediction. We can then confirm that that's a good prediction by measuring the overlap with the ground truth report, or to be able to extract different diseases from the predicted report as well as the ground truth and measure their overlap. These are ways of getting at the evaluation of these generative AI systems. An even better idea for radiology report generation might be to think of moving beyond the dot product between the image encoding and the text encoding. You could say, I want to learn a similarity metric. And in this case, that's what we did. We said, we're going to have a multimodal encoder that is going to be learned in order to help us understand whether an image matches a particular report better than it matches another one. We can take this one step further to say, can we teach a model to be able to answer questions about images by having it learn from textbooks? And that's what my colleague Michael Moore led in MedFlamingo, where we looked at textbooks which contain this interleaved data of images along with captions and text. And then we tokenized it and fed into a Flamingo style model to create MedFlamingo. The cool thing about MedFlamingo is that it can answer questions like these, where you present a case along with some information, ask a question, and have the model be able to spit out an answer with the correct diagnosis, and in this case, the correct pathology. One interesting benefit of training models in the way that MedFlamingo was trained is that you can do few-shot learning. And so in this example, we are able to give the model examples of what a good answer to a question looks like. And we can feed in 3 or 4 of these examples. And on a new example, we can say, here is a new CT scan, here's a new question, answer like I've shown you previously as part of your prompts, and the model can do that. The idea of a generalist medical AI really can enable a incredible change in the generation of medical AI systems, certainly that we're used to or have seen in the last few years. And as some examples, bedside decision support can be completely different, driven by natural language explanations of certain alerts. We can have grounded radiology reports where, along with generating a report, you can point to certain regions of the body that support that particular prediction. Or we can look at augmented procedures where in real time we'd be able to explain what's being seen through an endoscope, for example, to the proceduralist and be able to help them make decisions in real time. So I'll stop there. I'm at 10:25. There are a few resources that I'll leave up for those interested in the intersection of AI and medicine. In particular, if you're a clinician and specifically a radiologist, we are currently taking applications for the Medical AI Bootcamp. And there's other resources that I'll leave on this slide. So with that, that's my last slide. Thank you for having me, and I believe we might have time for questions.
Yeah, thanks very much. Yeah, we have time for questions. Feel free to either unmute yourself or ask in the chat and I can relay it. And I can get started while we wait for questions. I was wondering what your opinion is on, like, the methods you're using they're pretty cool. Some of them, I guess, come already from other domains. To what extent do you think what you're doing in the medical domain should be fundamentally different from other domains? For example, using CLIP to match text and images in a non-medical domain, and to what extent they actually are just the same?
Well, it's interesting you use CLIP as an example because CLIP was actually derived from the medical domain, taken into the natural domain, and then re-entered back into the medical domain, if that's a possible word. I think at some level we model for data sets, and we hope and we pray that our generalization of methods goes beyond the data sets that we apply them to. Part of the effort of the last 10 years of deep learning research has been to extend the scope of what we consider to be generalization, where initially it was multiple data sets for the same task. Then it became multiple data sets for different tasks. And that was specifically true in the NLP area, where we were combining question answering and natural language summarization. And then we went multimodal and we said we're going to combine tasks that look at images and tasks that look at audio and text. And I think eventually we go multi-domain, which is really what, is the ultimate form of generalization. But every time we do generalization, it also comes at the expense of being able to exploit structures that are specific to a particular data set and sometimes specific to a particular domain. So part of the challenge is if I want to have something work really well on medicine, I often have to forego it working really well on everything else. And that's a trade-off we accept. It's not a trade-off we might have to accept for very much longer. For instance, Whisper, which is the speech-to-text model by OpenAI, tends to do pretty good even with medical terminology, tends to do pretty good even with different languages. And I don't need a language specific model anymore, and that might be how it goes in the future. But as far as to get back to your original question, John, I think it's not as straightforward as saying what is something that's fundamentally new in medical imaging versus something that is fundamentally ported from some other field, because in some ways we're always standing on the shoulders of giants and making small